All right, so network topology today. All right, so here it is. Let me just queue up this. I think that's the big screen here. All right, so network topology. All right, network topology talks about the physical or the logical layout of a network. Most of the time you will be referring to it as to physical layout of a network as far as the connections, wired or wireless. And wires also divide into copper or fiber. Right? We will talk in the next, our next topic is going to be covering the copper links, and later on we will talk about the fiber optic or optical fiber links. All right, so now these are some of the symbols of that represent the different types of network connections physically, all right? Mostly physically. And I'll explain to you the difference between physical and logical type of a layout, all right? So ring, mesh, star, fully connected, tree, inline, chain, or a bus, okay? We will today concentrate on these four. These are the four basic ones. The other ones will be the combination of these four, more or less, all right? So ring, star, inline, or chain, or a bus topology. All right, definitions. Let's start with definition. Network topology. It's an arrangement of a network, including its nodes and connecting lines. And two basic ways of defining network geometry will be the physical topology or a logical or signal topology. We will expand on that soon enough today. All right, now basic elements of network presentation. On left side, we have something that's called nodes or hosts. And over here we have the connecting links. So the nodes or hosts would be something like computers, wireless access points, routers, switches, hubs, switches, hubs, bridges, gateways, and whatnot, printers and other devices. Let's not forget about other devices such as I don't know, it could be a climate control device or anything like maybe IP camera, right? Internet protocol camera. Right, so that would be the host nodes. It will be the smart devices that are connecting to the network. And then those are connected through links. And as always, we distinguish three basic types of connecting links. Will be copper, fiber, or the air. Right? Will be the radio waves. Okay. Then we have. Let's just start the analyzing a little bit of a ring topology. Okay. So in the ring topology, you could see the nodes here, and over here we have the connecting links. That's the arrangements, that's the symbol, more or less, of what it is. So in the ring topology, each node or host connects to two adjacent nodes. Okay, well, so this one here connects to two adjacent nodes. Simple enough, all right? In a continuous pathway for signals through each node, data travels from node to node with each node along the way, handling every data packet. Every node acts as a repeater. So there is no main server per se in this type of topology. All right, so there will be communication between devices, and it happens in this sort of a way. All right, now ring topology hardware. Here is a single port network interface card, and here's a double port network interface card. Which NIC could be used in a ring topology? All right, a single or double port. NIC stands for network interface card. All right, so of course, for the most part, if you are connecting things like a ring topology, you will have something to come in and something to come out of the same device. So this network card that this is the bigger card that that goes into the desktop devices such as computers. That would serve as a network interface card for a ring topology. You have to have an input and you have to have an output in order for this to work. Could a single one be used in a ring topology? No and yes. All right, but for the most part, no. Okay, because most of the time you're going to connect a network in a physical way, and there's no sense of routing the signal logically, so it goes from one to another in a way that it uses a single port. But it is possible. I just don't see any practical. Well, I shouldn't be saying that, but it is possible to trick the system into that single port for a bus. Here's a question here. Double or for chain as well? Yes. Single port for a bus? Yes, that would be true because the bus topology behaves, the signal routing behaves a little bit different than in the ring topology. Okay? Yeah, so most of the single port will be for the bus. Right? Now, ring configuration is just another representation of that. This is how signal travels, right? It travels in one direction in a ring topology. Now, ring topology applications, WAN or MAN. We will talk, these are the network types. Will be wireless area network, wide area network or metropolitan area network, for example. So here is a bunch of buildings. It will be a metropolitan area network. We will talk about the types of networks next time. So this would be a ring or a token ring. What is the difference between a ring and a token ring? You can see, just like analyze quickly what's happening here. These are buildings that have servers and communications nodes attached to the buildings, and some of the buildings are connected through a fiber line underground, like these three here. Then some of them are connected to each other through wireless antennas. Okay, so they're wirelessly, and the communication happens in this case. Over here, it happens in something that's called, if you want to picturize a token ring. The difference between a ring and a token ring would be that in a ring, the signal travels only one way. Here, only travels one way. Okay, now what happens if the link gets broken for some reason between one node and the other? Then the communication is broken from this computer on. All right, so the data would not be able to travel around the ring network. But if you're talking about token ring, is that if this computer tries to communicate with this computer, for example, and this link is broken, so it's going to try to send it that way, but it's going to notice, oh, there's a broken link, so let me try to send it the other way. Right, so this would be a token ring, so the communication goes both ways, in both directions. Right? So ring and a token ring, the difference is you're going to, I'm just telling you that because you will hear, most likely you will hear that type of a terminology. So now you know what the difference is between the ring topology and a token ring signal routing type. Okay. Now, applications for the ring topology, okay, would be LAN, which stands for local area network, which would be like a network that is installed in a building or a facility or a business. Right, now, when we're talking about switches and connecting links, okay, so when there's a bunch of computers in the field, or computers or nodes, which, because it could be not just a computer, it could be a computer, or it could be a telephone, a VoIP telephone, it could be a wireless camera, it could be a fire alarm communications module, could be security alarm communications module, could be nurse call station, could be all kinds of things that we generally would call them smart devices, right? So and those have to be connected somewhere, and the switches are capable of a certain amount of ports. There are 8-port switches, 4-port switches, 12-port switches, 24-port switches, 48-port switches, depending on how many ports the switch is capable to accommodate, because every node has to be connected to a single port of a switch. Now, if you have more devices than the switch is capable of handling, then you have to keep adding switches, and those switches have to be cascaded or connected in some sort of way, so they act like a one big switch. even though they're separate pieces of equipment, but they're connected to act like one sort of a central communication type of a node, right? So the switches can be connected in a ring topology, right? And of course, the signal routing most likely would be a token ring type of, I don't see a reason why the communication would not be traveling both ways these days right now, right? So you can see that one switch is connected to another, and then connecting to another, connected to another, and then the last one is connected back to the first one again, and type of a ring type topology, just like that here. Okay, so this is just another way of doing that. So here's a LAN application. Now, when you download this, you will be able to play the YouTube videos on hub switches and routers. So I want you to know the difference between the hub and a switch and a router. All right, just a 7-minute video. So go ahead and watch it later on, and then set up a chain topologies YouTube link. Play only up to minute and 42 seconds. All right, this is just an example of how things are connected in the real life. Right? So yeah, it's important that you watch these two videos. So here's 7 minutes, and here's here's 7.5 minutes. Here's 1.5 minutes. Right? So a few minutes out of your life, but if you don't know the differences between these, you should. Right? Now, star topology. We talked about the ring topology. Now we're going to be talking about the star topology. The symbol kind of changes from that, all right, into this, all right. So you can see that there's one main node, and from this node, all the nodes are connecting to it. So we call it as all these nodes home run to this one in the middle. All right. So what do we have here? Each node or host of a network is attached to a central node right here. Right? The central node is usually a hub or a switch. That's why I need you to know what these are. Okay. The central node can also be another proprietary device. What's a proprietary? It's a device of a specific function that works specifically with certain type of equipment. Right? The central node can also be another proprietary device, not necessarily a hub or a switch. It could be an NVR, which stands for Network Video Recorder, which is used with the security or surveillance type of the cameras. Right? In video surveillance systems. All right. Now, star topology is the most common physical wiring configuration considering horizontal network wiring. All right. The horizontal network wiring, keep that in the back of your mind. We will touch on in the next couple of slides. Again, I'm going to repeat this here. Star topology is the most common. Again, star topology is the most common physical wiring configuration considering horizontal network wiring. When you're connecting, if you end up working for a company that you'll be installing networks or setting up networks, this is what you'll be dealing with, which would be the star system configuration, which would basically what that means is that there are a bunch of smart devices such as PCs, wireless access points, and whatnot, whatever smart device is, they are going to be connected to one patch panel, which is going to be the next lab that we'll be talking about during the practical or from a practical aspect. And all those devices home run. Forgot to turn that down. All those devices home run to one central location. It's a pretty simple thing. You run a wire or a cable to every single device, and they all home run to one central location. Sometimes that central location with the main communications room or a LAN room, local area network room. Sometimes the wiring gets really busy in there, so neatness and proper structure as far as connecting the wires is extremely important when installing data networks, because sometimes in the communications rack, the equipment rack, you're going to have something like 600 wires running into it, and you have to make sense out of them. So labeling is important, and structuring them properly is important. So not only is going to work when you connect it first time, but it also can be serviceable whenever someone needs to do some changes or service to it. All right, so star topology. Here is another example of that. Here's a switch right in the middle here, and this would be the smart devices, and I just draw the computers here, but it could be anything else, as I said, as camera or security panel or fire alarm panel or whatnot. All right, star topology local area network. All cables home run to one point. And this is basically what it looks like in the real life. All right, can I zoom this thing a little bit? So this would be something that's considered, this is the back of a patch panel. Right? On both sides, this is a back of a patch panel or equipment rack, and this is also the back of the patch panel. So these all wires, these are so-called field wires. What does it mean that they are field wires? That means that they are running to the field. What's the field? The field is basically the rest of the building. So it could be different rooms, different desktops and whatnot. All right. So these are the field wires, and they all home run, and they are terminated at the patch panels. And then from that, this is the other side of the patch panel. We are using something that's called patch cords or patch cables, because there is a link between every single wire and some sort of a data outlet somewhere in the field, which means somewhere in the building. So there's a one-to-one connection, right? And there's a lot of them because they all home run to the same central location. And that we have to do something with it. So one-to-one, we are using patch cords or patch cables to connect every single port to whatever the port needs to be connected at the switch location, right? Or a hub. But then you're going to watch that video and you're going to be able to tell the difference between the switch and a hub, all right? So that's basically the idea of that. That's the modern type of network installations as far as the wiring structure goes. Okay. So what do they write here? Star topology LAN local area network. Patch cables are used to connect the panel ports to switch ports at their equipment rack location. Okay. Now, remember we were talking about horizontal wiring here. So there you go. Star topology local area network. Can you identify the star configuration? Well, on the first floor here, this will be a star configuration because all the computers run to the home, they home run to the central location, and the switch or the bunch of switches or the cascade of switches or group of switches would be located in this equipment rack. Okay, here's another floor. We're talking about the same network still, and there's another horizontal wiring. Right, so this is considered a horizontal wiring. In the horizontal wiring, the horizontal system or the horizontal part of the network would be considered the part that everything runs to the same rack location. If, for some reason, which I don't know why, but let's just say hypothetically, if one of those computers was located on the floor below, and that would be running through this floor into that one, so this computer would be considered of this horizontal wiring, right? But so that's basically that's terminology, okay? Horizontal wiring, okay? Now this here, okay, this connection right here between the communication rooms, and usually, excuse me. Usually, in big commercial buildings such as business high-rises or schools, hospitals, and whatnot, you are going to see the construction structure in a way that you're going to have something that's called a riser. All right, so the riser is that physical area that basically it just condensates all the communications closet one above the other, and this is the way things are being solved right now, right? So this will be considered the backbone, or if the whole thing is part of the same network, this would be part of the backbone, right? But for the most part, you're going to call this thing a riser, because you could have different types of different networks on different floors. And what do I mean by that? Like, for example, there could be an accounting department. They would have their own sub-network. There could be a shipping and receiving department. They will all have their separate network. There could be a management. They would have their own set, and so on. Okay. But it also could be part of the whole one big system with sub networks, or it could be the riser could accommodate many different businesses. So the wiring would just run from the bottom, for example, here, where there's the mouse, there will be this the beginning of the riser, and over here it says main cross connect, which would be maybe in another room or the room close to that, and sometimes it's in the same room right here. So this would be called the demarcation point, or demarc point, which stands for point of entry. Okay, so so the backbone would be like, for example, if you have one common network that is just exists on its own, and in that network you would have a point of entry, which is the demarcation point. So you could have a fiber optic line running to it, or a copper line, or maybe you're going to have a wireless transceiver, transmitter and receiver. So that would be the point of entry. This would connect to a modem. That modem would connect to a router or a switch or whatnot. So this will be the part of the backbone. Okay, and then the rest of that from the switch would be considered a horizontal wiring. Okay? So backbone is not necessarily the same as a riser, because riser is a physical area, so you could run your wires between the floors. Just remember that that term, riser, that's a physical area. And if you are installing networks, you're going to be hearing that a lot. Right, structured network cabling must, as I said, the star topology is the most popular as far as running networks. Okay, so this is another visual representation of that. What do we have here? We have the smart devices, PCs in this case, and here's a horizontal run, here's a horizontal run, here's another horizontal run. So this network consists of 3 computers, and that's it. And this goes into a one common patch panel, and the patch panel is patched or connected into the whatever device needs to be connected. Usually it would be a switch. All right, next slide. Now we're going to talk about the bus topology. All right, now all devices are connected in a single line. All right. It's just like tapping into a river with your water system. Okay. Now, what did I write here? I wrote the bus topology was used in a LAN setting until early 1990s. So that's how the computer networks were connected. There was no Ethernet per se, the cables that what we're using right now, you know, which we'll be using the RJ45, you know, those connectors that would look like overgrown telephone connectors. They're called RJ45 jacks. RJ stands for registered jack. Okay, so before that, and I still remember when I was in college, we would have that type of a network in our school, French college, right? And it would be utilizing a coaxial cable. So it would be just one main line with all the information there, and the computers would tap into that line, tap into that line, tap into that line. All right. So That's how it was done. So now I wrote this presentation in 2019, so I should probably change that. Presently, well, let's skip that 2019. All LAN, because it's 2021 right now. All LAN horizontal cables are wired in a star configuration. So now, okay, so what bus topology was used in the network. So why am I showing you this? Are we not using that anymore? Yes, we are using that, but not necessarily in the modern computer networks or LAN setting. Okay, but this bus topology is still being used in other applications. Okay? And that's the symbol for that. Right? Where is it being used? Okay, there's, oh, come on. All right, here is the transition. Now, so bus topology, although the bus topology is not used in the LAN settings anymore, it is still implemented in certain systems. That's what I wrote. Examples. This is the simplest way of explaining how the bus, this is the most, this picture here on top left is probably the visualization of the most primitive way of explaining on how bus topology looks like. It's, yeah, it is the most primitive way, and I'll show you how. I'll tell you why. Like, for example, this would be a fire alarm system. Right? How the fire alarm system works. A fire alarm system has something that's called zones, something's called zones. And the fire alarm panel would have, let's say, for example, it was with like an 8-zone fire alarm panel. What does it mean, 8-zone? That means it has 8 circuits that can notify you that there is something wrong, like a fire, right? Now, one of the circuit could be running smoke detectors along one hallway. The other circuit could be running heat detectors in the furnace room and so and whatnot. The other zone could be handling pull stations by the doors and whatnot, right? Another one could be handling smoke detectors in the air ducts and things like that. So each zone, this is like, for example, each zone is a loop, and it is a closed loop. All the devices, like this could be a smoke detector, this could be a heat detector or whatnot, doesn't matter what it is, they are in a normally open state, which means the system doesn't even see them. Now, whatever the sophisticated technology that goes into the devices is the technology that makes it recognize certain type of condition, like a smoke present or a heat present. Most of the time, that would be it. Or somebody pulls a door station, right? Like a pull station. And then, or some other device that senses, maybe a sprinkler was triggered and the relay was triggered from a sprinkler system, it's notifying the fire alarm, right? So all the technology, the sophisticated technology that is implemented in those devices is to make that thing trigger. But all the devices have in common, one thing in common, is that normally they are open. So this loop would not even see that they are in electronically or electrically. It's only when the device triggers, then the alarm panel will recognize this thing as a certain condition. Like there is a condition that react to it, right? So the system doesn't think, it doesn't have brains, it just has logical circuitry and it reacts in a certain way as it's programmed to do so. So this loop here is connected. So you just imagine those devices don't exist because the system doesn't even see them until they trigger. Then the system would only see something that's called a closed loop with something that's called an end-of-line resistor on it. And it has to have certain type of resistance that the system wants to see. And if that zone sees that resistance, then it thinks that everything is okay. Now there could be two conditions. If the line is broken, then the system is going to see an infinite resistance at its point, because this will be just a resistance of the air between them. So this would be more or less considered as infinite resistance for this for this purpose. So it is going to trigger something that's called a trouble condition. which means it's not a fire condition, it's a trouble condition, which means that the sensing circuitry is in trouble. So if there would be a fire, not necessarily the fire would be recognized by the system. So that manifests as some annoying beeps in the fire panel and repetitive annoying buzzing beeps. And whoever is in the building is going to be annoyed by that. They're going to walk up to it and they're going to see a light saying trouble flashing, and there's a phone number to call, which would be the service company who services the fire alarm, right? So but if the system, one of the devices triggers, like let's say there's a smoke here. Let's say this is a smoke detector. I can even see that myself. Let's say this is a smoke detector. This circuitry of that smoke detector detects smoke and it triggers, which means shorts it out. So then the system is going to see a short there. Now it's going to react as if there were a fire. So here's the main line. There are devices tapped into that main line. So this is the most primitive way of the picture or showing how the bus system works. Here's another system down below here, and this is a close-up of a security panel that utilizes bus communications. What do we have here? Here we have the part of the bottom left corner of a security alarm panel. And over here, we have something that's called green and yellow. All right, so this is using the old cable, old color coding. Remember the red and green and black and yellow, right? So it's using those cables, right? So it's using yellow and green for the signal type signal and on information, and most of the time you're going to see that red and black is used for power if you need to power up the devices. So each keypad is a smart device which requires to be powered, so it would have four conductors connected, the green and yellow for the signal part, and the red and black, which would go to right here, plus and minus. It will be connected just to power it up, right? So it would all be in one four conductor cable, but we're going to skip that red and black power because we're just going to assume that this thing has to be connected. Right now, green and yellow. Now, there is a certain type of communication going. There's a data flow. Right? It's just like, imagine this would be a radio operated system, and the air would be used as the bus provider. Right? But instead of air, we're using a couple of conductors. So this keypad is able to communicate with the system through these wires using whatever protocols it's using. And then this keypad is also able to communicate with the system through the same pair of wires. So here's the bus line, and here are a couple of devices. Now, with security alarms and other devices of this type, there could be other devices connected, like maybe zone expansion boards or some other devices that not only are keypads, okay, like door access control modules and things like that. So that's the idea of a bus, right? So even though the bus topology is not being used in the in the computer networks per se anymore, it is still being used in other applications. These are just the two. This is, well, I wouldn't even consider that as a bus, but it shows, it just gives a it makes it easier to explain what it is, to jump from this idea to that. Okay. Now, inline and chain topology. Right, here is the symbol of that. In this configuration, nodes are connected to each other through each other. Okay? Again, in this configuration, nodes are connected to each other through each other in chain configuration. All right, inline chain. Each node acts as a repeater. So this would be a ring topology, and this would be a chain or inline topology. There is no ring configuration. Right? See? So Chain topology is the one on the right here. As opposed to the ring configuration, the last device is not connected to the first device from a looped pathway. Where is this being used? Quite often you're going to see it in the industrial environment when there is a process logic or PLCs, process logic control, and you're going to see modules on one machine and a module, control module on another machine, and so on, and they could be connected to each other in this type of a chain topology. Right, so they can communicate with each other. Right. All right. Inline or chain topology. I'm going to give you some real life examples on how to visualize that inline or chain topology. For example, here you have we have on left side we have a switch, and we have a laptop or a PC and a printer. And on this side, on the right hand side, we also have a switch, we have a PC and a printer, right? So now these two devices are connected in a star topology to this switch. So this printer, or how is that being used? This printer could be a main printer in a big office. So it could be one big, huge, expensive printer capable of printing a lot of documents and fast. And instead of buying everyone a printer that is sitting on everyone's desktop, the company could just buy one main printer that once in a while somebody needs to get something printed, they would just send a signal to the main printer through the switch, right? So this will be the star topology. And this over here would be a configuration as if someone would have their own personal printer in their office. Okay, so this is a star topology, and this would be an inline or chain topology, these two pieces here, okay? Now, I'm also going to give you some real life examples of where you're going to see some of that inline or chain topology here. And by doing this, I'm not going to say device A or device B. I'm going to mention some devices that are being used in a real life. So that will also help you with distinguishing some of the devices, and maybe that's going to make you that much better of a service person or more informed. All right, so in inline, so this Ethernet extender is connected in inline with the Ethernet link. Why will we use something that's called the Ethernet extender? All right, Ethernet extender. So when it comes to utilizing copper wiring, the most distance we can get out of that is 300 feet. Anything above 300 feet end to end is considered a failure in the link, and the failure would be with the length of it. What happens is that if you have an Ethernet cable that is longer than 300 feet end to end, it's actually 328 feet. However, for the most part, we're just calling it 300 feet because just remember, you also have to use the patch cords and stuff like that. So that thing adds up. So that 328 feet is kind of designated for that. Right? So, but in some cases, when the link has to be longer, then we have to do something, right? It's either run optical fiber, which will be more expensive, or utilize or add something that's called a Ethernet extender. Why is it that we need to have 300 feet? Because if the cable is longer than 328 feet end to end, then the data is becoming unrecognizable at the other end. From either sending here, receiving there, or sending here and receiving there. Right? So that's the simplest way of explaining it. So there you could have a service call, for example, a large department store that would have a garden center somewhere with a cash register at the garden center, and it would have a service call saying that this cash register sometimes works, sometimes doesn't. It's very annoying because customers are coming with their payments, with the credit cards and debit cards, and sometimes it works and sometimes the system says that there's an error or something like that. So it's kind of inconsistent. So it would be a borderline length. Okay, I actually have a few of those in my career, if you can say that. So the simplest way is to utilize the Ethernet extender, so you can get another 300 feet out of that. Of course, the data is going to be slower, traveling slower, but sometimes the speed is not the most important thing. If it comes to sending a video signal or communicating through video and whatnot, yes, the speed is important. Or if you have one link servicing more computers that utilizing voice, video, and speed sensitive data like that, yes, it will be important to have the biggest speed you want, you can. But if it's something that's connected into cache register into the main switch, then the speed is not that much important, because at any given time you're just sending a couple numbers, few numbers, data string. It doesn't matter whether this thing is processed within a microsecond or is it going to take half a second. It won't even notice the difference, but it is possible to do that. So this Ethernet extender is connected inline with Ethernet link. All right, another one here, another device that you might see a lot in the future. It is called PoE injector. All right, it's connected inline with the wireless access point. What happens is that there's a wireless access point, which is basically a Wi-Fi connection, right? So this is in our college, for example, or in a building, you would have those wireless access points strategically placed in the ceiling or on the walls. So you could connect to them with your laptops wirelessly or your cell phones and whatnot. Most of that will be laptops or cell phones. Now, this device has to be powered, right? So what can you do? There could be a power adapter and they would have to plug it into the wall somewhere. But what if there is no power outlet somewhere in the ceiling? Usually there isn't. What you can do? You can call electrical company to have that installed there. But what if maybe 2 months later this thing has to be somewhere else? This can become a little bit messy, right? So what happened is that the power over Ethernet, the cable, the Ethernet cable, the computer, the data cable, is capable of carrying not only signal, but also a power to the device. So this is the DC signal, the DC power, and over that DC power, the signal is superimposed onto that. And the circuitry over there is just going to distinguish that. It's going to take the power and power up the device, and is going to extract the signal from that line and use the signal to communicate between it and whatever it needs to communicate. But some of the switches are capable of providing the power on their ports, and some of the switches are sold in a way that they are just signal, they're just data ports without the PoE, which stands for power over Ethernet, right? So if you're planning a system that utilizes security cameras, which need to be powered through the PoE, then you would purchase a switch that is capable of the PoE. But if there's an existing network that has signal running from between that switch and a bunch of computers that are basically plugged into the wall, then maybe there was no need for buying a PoE switch, which are more expensive. And the system worked fine. But at some point, somebody decides, oh, we need a wireless access point, but it needs to be powered of that. So instead of replacing the whole switch, you can buy a device that is called PoE injector, so power over Ethernet injector. So the signal is plugged into this PoE injector, and from then on, the wire contains the signal and the power. So it's called PoE injector, and it's connected inline with the whole system, right? Inline or chain topology, the good old VoIP right now, voice over IP, internet protocol, voice over internet protocol, VoIP. Those telephones, we are able to connect them separately, or they could be connected inline. Just think about it. When there's a company that has decided to retrofit their system, they probably have their old Cat3 telephone wiring for the old telephones in their walls, but they also have maybe at least one Ethernet jack that is providing signal to their computer. So when you're retrofitting or adding the system, changing the system from the conventional to the VoIP telephone system, you would have to plug in the phone not to the phone outlet, because it's not just a regular phone, it's a voice over IP, which is basically like a PC, but it just looks different. It has a, looks like a phone. It acts like a phone. But it's connecting through the Ethernet, connecting through the network. So the manufacturers that were presented with that problem decided that those phones can be connected inline. So you don't need to run additional Ethernet line to every office. It is going to help the client to make the decision easier to because it's all about money, you're selling things, right? That no additional wiring unless the wiring would be Cat5, right? Because the VoIP at present requires at least Cat5e type of a wiring in order to work. But if there's Cat5e, then you just plug in the phone into the telephone out, well, into the data network, right? And then it's just like a two-port network interface card. It has an input and it has an output. You will see those phones if you ever have a part-time job in like a Home Depot or Rona or some of the large department stores, Walmart maybe. You are going to see those POS stations, point of sale, which would be the cash register. Quite often you're going to see the VoIP telephone, and if you notice, there will be a data wire connecting the phone to the main data outlet, and from that it was going to go to the PC, which would be the cash register. That's one of the most common uses, or in the offices as well. Now consider PC0, PC1, PC2. Where are they here? PC0, PC1, and PC2. Are these PCs connected to the switch in a ring configuration, or is it a star? All right, of course, to this main switch, they're connected physically as a star, in a star configuration. And then there'll be like a router that is connected inline to the cloud. All right. So now here's the question here. Physically, it looks like it's a star configuration because it is, right? Can the system work as a ring? This is a highly hypothetical situation. It's just for you to visualize the whole concept. All right. Yes, it can work as a ring configuration, and I'll show you how it can be done. All right. No, here, let me just here, make it smaller here. All right. So physical topology. Here's a switch, and there are a bunch of nodes connected to that, and they are connected in a star topology. And the whole system can work as a star, but it can also work as a ring depending on how the switch is configured, because this now again it's a highly hypothetical situation. Then yes, it's possible to configure that. I don't know why would somebody do that, but hypothetically yes, it is possible. I just want you to see the difference between the logical topology and the physical topology. Right? So this is how it would work. Physical will be a star configuration, and logical it would be ring, as an example here, right? So that's how the signal would travel from one computer to another. So yeah, it would be a very inefficient way of doing things, but it is possible. Now, lab foundation, you're going to do the patch panel lab right now. So structure and cabling hardware. Now, what do we have here? And I highly recommend, or actually it's pretty much mandatory for you to watch the video that I sent you the email to watch that video, which would prepare you for the lab. If you don't watch that video, you're going to struggle with that lab. You're going to be very uncomfortable, and you're not going to get much out of this course, which you paid for, right? So please watch that lab video, which says patch panel. This is the rear of the patch panel. This is the front of the patch panel. And you're going to also see something like jacks, okay, data jacks. We already have dealt with that. And over here we have a couple of cables. One is Cat5e and one is Cat6 data cable. All right, so what will be the difference? If I zoom in, that see here that Cat6 cable, it has twisted pairs, right? but it also has a separator. So not only the pairs are twisted around themselves, but also the pairs are twisted around each other in a constant way. When we study this a little bit further, basically if you ever watch the Star Trek, some of the older episodes, the twisting the pair is just like creating a wormhole for a signal. So that's basically that's the idea. It gets most of the main reason for having a pair that's twisted is to eliminate interference from other pairs and a crosstalk between the pairs. Right? Crosstalk is basically a signal bleeding from one pair to another. And this is a Cat5e cable, also has a twisted pair, but it doesn't have that separator. Right? So that's now you know the difference between Cat5e and Cat6. Cat6 and up, basically, right? Now, insulation displacement connection, we talked about that. Here's a bit of a history spill here. This is how the insulation displacement connection works. It has a connector that is like a knife-shaped connector, and you punch in the wire, and though that connector bites into the insulation, makes a connection with the wire. The only thing that I got this thing from the internet, you don't use that on the stranded wires. It has to be solid wires. So somebody put it up on the internet by mistake using the stranded cable. All right, so that's pretty much it. You have 5 minutes to get to your next class, and I will see you next. I'll see you next time. And please watch the video that is demonstrating how you're going to use the next. So I think this is, you're still doing lab 2, and you're going to, but you have ahead a lot of time to watch that video. All right, it's a little bit lengthy, but trust me, it's worth it. All right? Cool. All right, thank you very much, guys, and I will see you next time. Have a good one.